Converting a binary number like this to decimal, you might think is not that complicated. Each digit has a particular place value. I can write those down here. And in this case, we've got a 1 in the 2's place, in the 8's place, and in the 32's place. So if you add those up, 32 plus 8 plus 2 equals 42. So that's easy enough, right? Well, maybe for you, but that's not how computers do it. So if a computer like this has a number in its memory, and of course, it's going to be encoded in binary, how does it turn that number into something like this that us humans can read and understand? It can't do the same thing we did, because what would that even mean? We just added up the place values to get 32 plus 8 plus 2 equals 42. But doing that assumes, some familiarity with decimal. A computer isn't going to look at 32 as 32. It's going to look at it as 1, 0, 0, 0, 0, 0. And it's going to look at 8 as, 1, 0, 0, 0. It's going to look at 2 as 1, 0. You add all that up and you get 1, 0, 1, 0, 1, 0. You're right back where you started. So how does a computer do it? How does it get this decimal number? And by the way, if you're envious of my extremely capable computer and its ability to display numbers, you can build your own. I've got a whole series of videos where I walk through building it with the 6502 processor, the ROM, the RAM, I/O, the display, and everything. And you can also check out my website where I sell kits with everything you'll need to build your own. But at any rate, if you think about what a computer has to do to display a number like this as decimal, it's got to come up with all of the separate digits of the number. And in fact, right now, I'm totally cheating. The code is literally printing the character 4 and then printing the character 2. So it's totally not reading the value of 42 from anywhere. Now, I could make this a little bit fancier and print out zeros for both of these and then add 4 to this one and add 2 to this one because, the character for 0 plus 4 is going to give us the character for 4. The character for 0 plus 2 is going to give us the character for 2. In fact, I could even represent the 4 in binary like this and the 2 in binary like that if I want to get even fancier. And this is still going to print out 42, but it's still not starting with the number 42 anywhere. We've already done the hard part here of breaking up the 4 and the 2 as separate digits. But maybe we can get the computer to do that. One approach might be repeatedly dividing the number by 10 and looking at the remainders. So for example, if we start with a number like 1729, let's say, if we divide that by 10, we're going to get 172, and we get a remainder of 9. And if we keep dividing, so we take the 172 now, and we divide 10 into that, well, 10 is going to go into that 17 times, and we're going to have a remainder of 2. Well, now if we divide 10 into 17, keep going here, 10 is going to go into 17 one time, and we're going to have a remainder of 7. And if we want to keep going, we can try to divide 10 into that 1. Of course, 10 is going to go 0 times, and we have a remainder of 1. But if you look at these remainders here, we broke the original number, 1729, up into 1729. So that's great. But there are just two problems. First, we're still working in decimal here. And the whole point is that we're going to be starting with binary. But we're just doing division. So presumably if the computer wants to divide numbers, it's going to do it in binary and work just fine. Except that's the second problem. The computer doesn't actually know how to divide. The only arithmetic instructions that the computer knows about are adding and subtracting. And that's basically it. I guess there's also increment and decrement. But basically all the CPU can do is add and subtract. But fortunately, it turns out that doing division in binary doesn't actually involve doing much division. And I'll show you what I mean. So let's say we've got this big, long binary number here. This is a 16-bit number, and we want to divide it by 10. Well, 10 is 1010 in binary, so we want to do this division problem. And if you've ever wondered, when am I ever going to need to know how to do long division? Well, you're in luck, because we're going to do some long division. And so if you remember, the way that you do long division is you sort of work your way left to right here. So we're trying to divide 10, or 1010, into here somewhere. And the first place it divides is actually right here, this 1101. And so it goes into that one time. And if you remember how to do long division, you got to make sure you kind of keep everything lined up because it's all about place value. And then we multiply. So 1010 times 1 is going to be 1010. And then the next thing we do is we subtract. So 1 minus 0 is going to be 1. That's easy enough. 0 minus 1 is a little harder. We've got to do some borrowing. So what we'll do is we'll take this to 0, and then we'll borrow a 1 over here. So now we have 1, 0, minus 1. So this is effectively 2 minus 1. So 2 minus 1 is going to be 1. And now we have 0 minus 0 is 0. 1 minus 1 is 0. All right, so easy enough. The next thing we're going to do is we're going to bring down the rest of this here. So we bring down this 1, we bring down the zeros, and this final 1. So now we've got this new number down here that we're trying to divide into. And so again, we kind of keep going along looking for somewhere where we can divide the 1010 into it. And the first place it's going to go in is this 1110. And so 1010 is going to go into 1110 one time. So I'll put a 1 up there. And then we'll subtract. So 1010 times 1 is 1010. And subtract that off. And so 0 minus 0 is 0. 1 minus 1 is 0. 1 minus 0 is 1. And then 1 minus 1 is 0. And actually, as we go along here, we could fill in some zeros up here. But then again, the next step is to bring down the rest of this. So we'll bring down these zeros and look for the next spot that 1010 divides into it. And actually, it's going to be this here. And that's going to divide into that 1 time. So I'll put another 1 up here and then multiply that 1 times the 10 and do another subtraction. So 0 minus 0 is 0. 0 minus 1, we're going to need to borrow again. So this is actually going to become a 2. So 2 minus 1 is going to be 1. 1 minus 0 is going to be 1. 1 minus 1 is 0. And then, of course, this went to 0 because that's where we borrowed. So we're left with this bit here. And then next we can start to bring down the rest of it. And our 1010 is going to go into 1100 one time. So I'll put a 1 up there, put our 1010 down here, and subtract again. So 0 minus 0 is 0. 0 minus 1, we're going to need to do a little bit of borrowing here. So 2 minus 1 is 1. 0 minus 0 is 0. 1 minus 1 is 0. Okay, we are almost done. So now we bring down our 0, 1. And actually, we are completely done because 1010 does not go into 1001. So if we put in the rest of our zeros up here, this is the result of our division problem. So we divided this big long binary number by 10, or 1010, and we got an answer. But of course, we're interested in the remainder. And the remainder down here is this little bit. And that's going to be one of our digits. In fact, that's going to be the first digit here, which is a 9. So this is actually a 9 in binary. So we're kind of seeing the same thing here. And then this number up here, if we were to sort of decode that, we'd find it's 172. But now we need to do the next step here. And that works just the same way. So if we take this same number over here and divide it by 10 again, we can keep going with this process. This goes in 1 time, 1010, subtract that, 1100, bring that down. 1010 goes in there 1 time, subtract that, fill in some extra zeros up here, and now we get a result of dividing that, and our remainder down here now is a 2. So this was a 9, remember? Now we have a remainder of 2 in binary, of course. And then the next thing we want to do is we take this and divide it by 10 again. So here it is. And these problems are becoming a little bit easier. It actually only goes in 1 time. And if we subtract off the 1010, 1 minus 0 is 1. 0 minus 1, we need to borrow. So this becomes a 1. This becomes a 1. That becomes a 0. So we borrow. 2 minus 1 is 1. This is a 0, this is a 0, this is a 0. So we have a remainder now of 3. And we're left with 1, and we can do the final division where we divide 10 into 1. And of course 10 doesn't go into 1 at all, so that's a 0. If we subtract, we're going to end up with a remainder of 1. And so our final remainder is a 1. And it looks like I probably did something wrong here because I'm expecting 1729 and I got 1329. So I probably did something wrong here. Let me take a look and see. You probably noticed it already. Oh, of course, there it is. So this, we borrowed a 1. So that was actually 1 minus 0. This should be a 1. And then, of course, 111 is not 3. It's 7. And so we could do all of these operations in binary, which is great. We end up with, if we're looking at the remainders, we get 1729. Which is the actual number that we started with over here, 1729 in binary. But again, all of this assumes that we can do division. But I hope what I was kind of trying to show here is that we were able to do the division without really doing division. I mean, at no point were we really dividing anything. It was mostly a subtraction, which is good because that's what our computer can do. It can do addition and subtraction and not a whole lot else. But how do we actually translate these division problems into assembly code that can run on a computer? Well, let me actually show you a different way of representing these exact same division problems in a way that is actually going to be easier for the computer to do. And to make this a little bit simpler to see, I made this little simulation of the algorithm that we can sort of step through. So what I've got here is, if you look at the 16 digits over here on the right, that's the number we're starting with. And what I've done is I've added another 16 digits over here to the left of it. And then I've also got the 17th digit out here, which is the carry bit. And you'll see how that gets used here in a minute. And if you think about what we're doing with long division, we are essentially taking this 1010, and we're kind of sliding along here, looking for a spot where we can divide it in. And another way to think of that is to think about sliding this number here to the left. And so that's what we're going to do, is we're going to do a rotate left operation, which is something that is very easy to do in the CPU. You just shift all the bits to the left. And then what we're going to do is we're going to look at, by rotating to the left, what we've done is we've pushed the first bit, which was a 0, into this left half here where I've got 16 bits. And we can use those 16 bits to kind of look at, okay, does 1010 divide into 0? Of course, the answer is going to be no. But we can try that by subtracting. So what we can do is we can do a subtract with carry. And what we're going to do there is it'll set the carry bit, and then we'll try to subtract 1010 from whatever we've got in here. And by setting the carry bit, that gives it something to borrow from. So we're going to try to subtract from 0. So it's going to need to borrow, and it's going to keep needing to borrow until it gets out here, and then it has a bit to borrow from. And so the result is going to be a whole bunch of 1s that had to be borrowed, and then some stuff over here. But the nice thing about this is we can then look at the carry bit and see, did we need to borrow something? And in this case, yes, we did. And by looking at that, we know that, okay, well, if we had to borrow something, then we weren't able to actually, or if we had to borrow something from all the way over here, I guess I should say, then we weren't really able to subtract 10 from this number. We weren't able to subtract 10 from 0, or we ended up with a negative number, I guess is another way to look at it. And so because of that, we can say, well, okay, 10 didn't go into 0, which, no surprise. So we'll just ignore this result, and we'll repeat the process. So we'll shift this over. We'll subtract 10 again. We get kind of the same thing because we're still subtracting 10 from 0. So we'll just ignore that result. And we'll keep shifting this over. Subtracting, it didn't work. Rotate left. Subtract, didn't work. Rotate left. Subtract, that didn't work. Rotate left. Now it's getting a little bit more interesting because now when we subtract, we're subtracting 10 from 1. It's still going to be less than 0. We didn't get anything, so we're still going to ignore that. But at least we're getting a different answer. Now we've got 3 here, so we subtract 10 from 3. That's still not going to work. Now we've got 6, so 6 minus 10, still negative. But now things get interesting because we've got 13 here, right? 1101 is 13. We're going to subtract 10 from that. And when we subtract 10 from it, we get 3. And the other thing we get is the carry bit that we put in here doesn't get borrowed from. And so we can look at this carry bit and we can say, our subtraction worked. In the sense that we got a positive number. And since really what we're trying to do is division, we're trying to see, does 10 go into 13? Well, yes, it does. It goes in 1 time, which, it's binary. It's either going to go in 0 or 1 times. So this tells us that yes, it goes in. It goes in 1 time, and that's sort of what our carry bit is telling us. And then when we do the subtraction, we get 0011. So we're basically at this step of our long division. So the next thing we're going to do is we want to start now looking, we don't want to look up here anymore. We want to do that subtraction. We've done it. We want to bring down the rest of this because that's the next step we do if we're doing long division, is we bring this stuff down and then start trying to divide into this number here. So in this case, instead of bringing it down, because we're kind of working with this 32-bit, this 32-bit thing in memory here, what we can do is we can just copy this or store this result back up into the left half here. So we'll take all these zeros with the 1, 1, with the 3 here, and we'll just put that up here into our result. And there we go. And so now, essentially we're kind of looking at this row here and continuing with our long division by looking at, okay, where does 1010 go into this? So we'll rotate. I've got a 7 here. 10 doesn't go into 7. We'll ignore that. Rotate again. We've got 14. 10 does go into 14. So when we subtract, we get 4. And we didn't use our carry bit, so we know that it actually went in. So in this case, again, we're going to hang on to this result. So we're going to put this result back up here. So we'll do that, store it up there. And now if we look at what we've got here, we're kind of down on this row here, right? We've got 1, 0, 0, 0, 0, 0, 0, 1, right? And we'll keep moving along. So we'll rotate left. We've got an 8. 10 doesn't go into 8, so we ignore that. We'll shift again. We've got 16. 10 does go into 16. If we subtract, we get 6. And so we'll hang on to that. So that's this subtraction here. And I guess the other thing to notice is, we've been kind of looking down here, but we also want to record the result of our division. But the neat thing about this algorithm is that every time we're able to successfully subtract something, we wind up like this with a 1 in the carry bit. And so when we do that rotation, that 1 ends up getting pushed in over on this side here. So as we're kind of moving through our original number, shifting this over, the answer is sort of popping in here behind it. So we've got a, 10101 already in there. We've got a couple more digits to go. So let's keep going. So we've got 1110, that's here. So we're going to do this subtraction. We get 10. So we'll store that result. We'll push this 1 in over here. So now we've got this 101011 part of our answer. And then we'll do another attempt to subtract. Can't subtract. Ignore that. We'll rotate again. Try to subtract. Not able to subtract. So we'll ignore that. And at this point, we've shifted 16 positions. So we've shifted the entire number all the way through. That's what this little counter here that says 16 is. And so once we've done that, we know that we are done with our division. And if we look here, we have 1001, and that is our remainder. So we've got a remainder over here. And once we shift that last 0 over here to this side, we get the answer to our division problem over here on the right. And the cool thing about that is because our answer is over here on the right, we're all set up to do the next division problem. So we've recorded our 9, our remainder, so we can clear that out. And we're set up to do the next division problem. And so if I just go power through this, we can just go through all 16 steps, and it's doing the same thing that we were doing before. Now we're finally getting into something here. So the 1010 minus 1010 equals 0. That's this first subtraction. So we'll store that, and we get our first 1 going in over here. And then I'll just keep going. Nothing's happening. Nothing's happening. We get to the last spot here. And there's our remainder. So our remainder is 10. That's 2 in decimal. So we've got our remainder. So if we do our final rotation, then that 1 goes in over here, and we've got our answer. So we were able to get the remainder as 2. And now, once we clear out that remainder, we are set up and ready to go with the third division problem to get our next digit. And so we're still going to go through all 16 bits. Now the first bits are zeros, so they aren't very interesting. But we will finally get all the way to the end here, where we get to 16. And here's the subtraction that we actually ended up doing here. And the computer did it right, go figure. And it gets a 7. And so we'll store that. And there we go. We've shifted all 16. So this is our remainder of 7. So we could keep track of that there. And then we can do the final rotation to put the last bit of our answer in over here. And if we wanted to, we could do this last problem here, which is not going to be very exciting, but just to show that the same algorithm works. If we shift through this 16 times, it's going to get a whole bunch of zeros. And then eventually it gets to the end. And we subtract. We still get another 0. But we've been through 16 times, so we know that our remainder is 1. And so that's our final digit. And then if we do that last push to push that 0 in over here, we have all zeros over here. And so that's actually kind of how we know we're done. So by going through this fairly straightforward algorithm that only uses 4 bytes of memory plus the carry bit, we were able to, through the course of that with maybe some, basic conditional logic, we're able to pick out the digits of the original number, 9, 2, 7, and 1. And we just need to flip the order around, I guess. And so hopefully you can see how this algorithm that I just stepped through is doing effectively the same thing as the long division. It's just that, instead of writing everything out, showing our work, I guess, we're able to kind of do it all in a very compressed amount of memory. And we're also able to do it with things that we know that the CPU is able to do, rotate left, subtract, conditionals based on whether the carry bit is set or not. Those are all things that we're able to do with our CPU. So let's actually try to translate this algorithm into code. So this is the program I was running before that's totally cheating, just writing the 4 and the 2 separately. But the rest of this should look fairly familiar if you've been watching some of the other videos in this series. I start out by resetting the LCD display. Actually, at this point, as soon as the LCD is initialized, then we jump into this infinite loop here. So we'll add some additional code here to actually do what we want to do. Below here, I just have a bunch of subroutines for printing stuff to the LCD, sending instructions, and so forth. Again, if you've watched some of the previous videos, this should all look familiar. But now what we need is some space in memory to store this data. And we've got two 16-bit values. So this is actually going to be a total of 4 bytes in memory that we need to store. And we can't just store these things in CPU registers because there aren't enough CPU registers to store all this. So we do need to put this in RAM somewhere. And on this computer, the RAM is everything from address 0 all the way up through address 3 FFF. So we just need to allocate a couple spots in memory for the data that we want to store. So we have the value itself, and I'm going to store that at address 0200. And that's going to represent this right half here. That's going to be the value. And then we also need this left half, and I'm going to call this just mod 10 because that's what it sort of becomes once we apply this algorithm. So I'll put mod 10 at address 0202 actually, right? Because each of these is 2 bytes. So value is going to be 0200, 0201. Mod 10 will be 0202 and 0203. And so maybe I can just add a little comment here to say that each of these is 2 bytes. So once I have that memory allocated, let's go down here to where we're actually going to be doing stuff and initialize it. Oh, and I guess one other thing I need is I need the actual number. So at the bottom here, so we have our infinite loop. That's how we're going to halt the computer when we're done. But down here, and this at this point we're in ROM, I can put the number that we actually want to convert. So we'll just say number is a word, and we can use that 1729 example again. And I guess it's sort of silly. I'm typing it in here as decimal, and of course the assembler is going to turn that into the binary image that we put on the ROM, and so it'll be binary on the ROM, and we're just going through all this effort to convert it back. But anyway, that's the number that we'll convert. We'll have that in ROM. And when we first start out, what we want to do is we want to copy that number into RAM, where we can start to manipulate it. So what I'll do is I'll just load the number into the A register, and then store that as the value, and then load the second byte of the number, because it's a 2-byte, 16-bit number, into the A register, and store that into the second byte of the value in RAM. So now we've got our number in RAM, so that's the right half here. So we've got that all set up there. And now the left half, we want to initialize that to 0. So we'll load a 0 into the A register, and then store that into the mod 10, that's the left half, as well as mod 10 plus 1, which is the second byte of that left half. So now we're set up like this. We've got our value in memory here. We've got all zeros over here. The first thing we're going to do is we're going to do this rotate left, right? So we want to rotate all of this to the left through the carry bit. And we can use the carry bit to do that because we actually need to rotate each byte. There's actually 4 bytes in here. So if we rotate the first byte over here, this will be the first byte of our value. If we rotate that left, then it'll take the carry bit, put it in on the right side, rotate it left, and then the leftmost bit will go back into the carry bit. Then if we rotate for the second byte of the value, then that'll take the carry bit, put it in that, and then the leftmost bit will pop out into the carry bit. We could do that again for the value, and if we do all 4 of those, that'll rotate this whole thing, just as we've been kind of looking at here in the simulation. So the way that looks is we rotate left the value, and then we do the same thing for the left half of the value. And then the carry bit coming out of the left half of the value goes into the right half of mod 10. And then that's going to rotate into the left half of mod 10. And so doing all that is going to do this rotate left. It's rotating all of these things left, with the leftmost bit going into the carry bit at the end, and with the carry bit going into the right at the beginning. And I guess I could start adding some comments here just so we know what's going on here. So the first thing we're doing here is we're initializing value to be the number that we want to convert. And then here we're just initializing the remainder to be 0. And then here, our rotate here, we're rotating the quotient and the remainder, just like we saw. So now the next thing we want to do is we want to subtract 10 from the mod 10 part of this over here. So this left half, which I'm calling mod 10, we want to subtract 10 from that. And of course, we're dealing with an 8-bit processor, so we can only subtract from 8 bits at a time. So we're going to need to use the carry bit again. So we'll set the carry bit because we want to know if we had to do a borrow. And then, of course, we're going to do a subtraction. We have to do that in the A register. So we'll load the value from mod 10 into the A register. And so that's the right half of this left part here. So it's going to load these 8 bits here into the A register, which, for the first example, here's all zeros. And we're going to do a subtract with carry of 10. So we're going to subtract 10 from whatever value's there. And so that'll give us this part of the answer, but now we still need to do the rest of the subtraction over here on the left. So let's actually take the answer that we've got in the A register and put it somewhere else. So I'll transfer from the A register to the Y register. That way we can kind of save the low byte of the subtraction in the Y register. And then we'll load the high byte that we're subtracting from into the A register and do another subtract. This time we're subtracting 0, because we subtracted 10 over here, but if we're looking at what we're subtracting over on this side, implicitly these are just all zeros in here. So we're subtracting, 0 from whatever's in the top. And then the result of that is going to end up in the A register down here. And so once we've done that, we'll have our answer basically in a combination of the A register and the Y register. So if I want to add a comment here, the A and Y register together now have the contents of the dividend minus the divisor. So it's the result of that subtraction that we're doing. So now at this point, what we want to do is we want to say, well, in this case, we want to ignore the result, but we want to ignore the result because the carry flag ended up being cleared. So because we had to borrow in order to do this subtraction, which means that the dividend is less than the divisor. So when we subtracted, we would have gotten a negative number. So we need some conditional logic, but the conditional logic is going to be based on the carry flag. So if our carry flag is clear, like it is here, then we want to ignore the result. And we can do that with the branch if carry clear instruction. So we want to branch if the carry is clear to somewhere else. So we can do branch if carry clear, ignore result. So this is we're branching if the dividend is less than the divisor. And we're going to branch to ignore result, which will be down here. But if we don't want to ignore the result, then what do we want to do? Well, in that case, that means that we're in one of these situations where when we subtracted, we actually got a positive answer. So let's do this subtraction here. We subtract, we get 3. So here the carry is not clear. So we're not going to do that branch of carry clear. So what do we want to do in this case? So in this case, we want to take the result that we have, which again is in the A register and Y register, and put them into this mod 10 position up here. We want to put that up here. So we can store the contents of the Y register in mod 10 and store the contents of the A register in mod 10 plus 1. So that stores this dividend minus divisor, that result, which is in A and Y. It stores A and Y into the mod 10 part of our memory. And of course, if our dividend was less than the divisor, then we just skip that. We skip over that. We come down here to ignore result. But then either way, once we've either ignored the result or in this case stored the result, the next thing we want to do is basically just repeat that. We want to do another rotate left. We want to do the subtraction again. We want to do everything again. So at this point, what we need is a loop. And so what we can do is we can go all the way up to the top here where we started. So let's see, this is initializing our display. We don't want to reinitialize the value. We certainly don't want to reinitialize the remainder to 0. But right here, right before we do the rotate, we want to start a loop. So we can do that by just putting a value in the X register, which we're not using yet. So we can put 16 in the X register, and then what we'll do is we'll just decrement every time through the loop. So we'll put 16 in the X register, and then we'll start our loop right here. And then at the bottom, once we either store our result or we jump past the storing the result and ignore the result, either way, we then want to decrement X because it starts at 16. We're going to decrement it all the way down to 0. And once it hits 0, then we want to stop this loop. But otherwise, we want to just jump back up to div loop. And I'm going to use the BNE or branch not equal instruction, because the way that works is it branches if the 0 flag is not set. And so if we decrement X and it's not 0, then we'll loop back up here to div loop, and we'll go through this process again. And we'll go through the process 16 times because X is starting out at 16. I guess one other thing that we should do here to initialize before we get into the loop is to clear the carry bit, because when we start out, everything is cleared. In fact, maybe that's sort of more part of initializing the remainder. So we loading a 0 into that mod 10 plus 1. We also want to clear the carry bit, make sure that's 0 before we start. But then, yep, we got 16 in here. We're going to go through this loop 16 times and then either store the result or ignore the result based on whether the dividend was less than the divisor. So that's just doing what this model is doing. It's going to go through it 16 times. And so when we get to 16, we're going to do that final subtraction. In this case, we're going to ignore the result. So that would be that branch if carry is clear to ignore result. And then after we ignore the result, we throw that away. This is the state we're in now at the end of that loop of going through 16 times. And here we have our digit, our first digit here. So if we want to output that remainder, we can do that right here. So the remainder is going to be in that lower half of the mod 10 variable. So if we do load a mod 10, that's going to get that into the A register. And of course, this is just going to be a binary number from 0 to 9. That'll be the digit we want. If we want to display that as an ASCII digit, kind of like I was doing before, we need to add the value of an ASCII 0 to it. So we could add the value of a 0 to the A register. And actually, this is an add with carry, so we want to make sure we clear the carry a bit before we do that add, so we get the right result. And so now we're going to have an ASCII number from 0 through 9 in the A register, and we could just jump to our subroutine to print that character, and that'll put that on the screen. So now that we've got this value, the next thing we do is we do another rotate. So we need to do one final rotate to get the carry bit back around here, because we don't quite have our answer yet. We've got that one last result bit that needs to be rotated in over here on the right. In this case, it's a 0, but it could be a 1. So we'll rotate that in, and now we have our answer, right? That's the actual result that we were trying to get. So we need to do one more rotate. Although we actually, we have to be careful we do that before we do this clear the carry bit, because the thing we're rotating in is the carry bit. So we want to rotate the carry bit in before we clear it here, and also hopefully without mucking up our mod 10. But we should be able to do that, because if we rotate the carry bit into the bottom of value, that's not going to mess with mod 10. And then we need to continue that rotation into the top half of value. But if we stop there, then we won't actually rotate anything extra into mod 10. So mod 10 will still have our answer, and then we can clear the carry bit and we can do our add to convert that to an ASCII character from 0 to 9 and print everything, and that should work out fine. So at this point, if we halt the program, it's just going to print one digit, and of course we would like to print the entire number. But everything's set up. We can do another division problem. We just have to have some sort of loop that takes us back to the right place where we can set up for our next division problem. And we obviously don't want to rewrite this part here, but we do need to clear the remainder. So right now our remainder is has got some stuff in it, and we want to set that to all zeros. And we've got the code for that already. We just need to jump back up there. So the spot we need to jump back up to is right up here where we initialize the remainder to 0. So this is where we do another division problem. So we want to jump up to divide down here at the bottom, but we only want to jump up there if we're not done. We don't want to just keep going up there forever. So how do we know that we're done? Well, we're done when the result of our division problem is a 0, right? Because when we divide and we get a 0, of course, the remainder is going to be the last digit we're looking for. But the result is going to be a 0. That's how we know we're done. Because all these other cases, the result is, it's something else. And we feed that into the next division problem and the next division problem. But then when we get a 0, that's how we know we're done. So we want to check to see if the result was 0. Well, the result is going to be in this value here. So we just need to look at the two 8-bit chunks of that. And if any of those bits are set to a 1, then we know we're not done. We want to jump back up to that divide label that I just added. So if the value is not 0, we want to continue dividing. And to figure that out, we could load value into the A register, but we also need to look at value plus 1 because we want to look at all 16 bits of the value. And all we care about is whether any of the bits are set. So if we just OR the A register with the top half of value, so essentially we're doing a bitwise OR of the bottom half of value and the top half of value, we're ORing those together. If any bits in either the top half or the bottom half are set, then the value in the A register will have some bits set. But if all of them are zeros, then the A register is still going to be a 0 at this point. And so we can use that to say, branch not equal. So branch, if the A register is not equal to 0, effectively, then branch not equal up to divide. So in other words, if value, all 16 bits of it, is not 0, then we go back up to our divide up here, which we will initialize the remainder to 0. We'll load the X register with 16 again, so we'll go through 16 iterations of our division loop, which will just go ahead and compute the next value. And so once it goes through 16 iterations of that division loop, then it's going to print out the next character, which is going to be a 2. That's the next result that we're going to get. And then rotate that last bit in, and then we're set up for the next division problem. And it's going to keep going until we end up with all zeros here, like we saw before. So if I didn't make any mistakes, hopefully this will do something that will print out the number that we started with. And the number, again, is 1729. I just have that defined here in ROM to start with. So let's save that, and I'll run the assembler, and I'll go ahead and write it to the EEPROM. And now let's give it a try. Put the EEPROM back in our circuit. Power this up. Reset. And, well, that's almost the right answer. We wanted 1729, but we got 9271. And, of course, that makes a ton of sense because we're calculating these backwards, right? We calculate the 9 first, so there it is. Then we calculate the 2, then we calculate the 7, then we calculate the 1. So it's printing them in reverse order. So our next challenge will be to flip those around. So what I'm actually going to do is I'm going to create a string that will build one character at a time. And the string is going to be in memory. And if you've watched my videos on writing a Hello World program, you know that I ended up using a string that had the string Hello World in it. And I was able to print that out pretty easily. Well, it took 9 videos, but I was able to print that out. But this time I don't want the message to be in ROM. I want the message to be in RAM. So I'll create another variable here. And I guess this could be up to 6 bytes long because, you know, we're working with a 16-bit number. So it could be as high as 65535, which is 5 characters plus a null termination. So message could be up to 6 bytes, but it starts at 0204 in RAM. And we want to initialize it. I guess we can initialize it up here. And we'll just store a 0 in the first byte of the message. So that way, you know, it's a null terminated string. So if we just store a 0 at the first position, then it'll be an empty string. And then what we want to do is instead of printing a character, wherever the point is, down here where we normally would print the character, instead of doing that, what we want to do is basically push the character onto the front of our string. So instead of print char, we'll say push character. And then I need to actually write that. So push character will be a subroutine that we'll write. We can put that down here. So what do we want to do here? Well, when we come into the subroutine, we're going to have a character in the A register. And we want to take whatever that character is that's in the A register and want to add it to the beginning of the null terminated string that is pointed to by message, or that's in memory at the message location that we just defined at the top. And so to do that, we're going to have to kind of go through message and move each character over to make room, and then put the new character at the beginning. So since we're going to need to move a bunch of characters around before we get to the point where we can put the new character at the beginning, let's start by pushing the new character onto the stack. So we'll push A onto the stack. So the character that's now going to be the first character of the string, we're going to push that on the stack because we need to come back and deal with that later. That way what we want to do is basically just go through and loop through the message and move each character over one. So I'll start out with a counter y and start that at 0, and that'll be the index into the message. So then we can load the first character, or I guess the y character of the message, because this is eventually going to be a loop. We can load that into the A register and then transfer A into the X register. So basically we're going to get a character from the string and put that into the X register. Then we can pull the character off the A register, so that's the new first character. We can pull that off the A register and put that as the first character of the string. So now we've taken the original first character from the string, put that in the X register, and now we're replacing it with the new first character that we want to push onto the beginning of the string. So once we've replaced the first character of the string with the new first character, we can increment y to move to the next character. So now we're moving to the next character, and we have the new character that we want in that next position. That's already been pushed on the stack, so we're kind of ready to go into a loop here. Well, actually, we're not quite ready yet because we don't have it on the stack yet, because we have the character that was the first character. We have that now in the X register. So now what we want to do is we want to put X back in the A register and push that onto the stack. So there we go. Now we've got the character that was at the beginning of the string on the stack, and the character that was on the stack is now the one at the beginning of the string. And so now we can go through this loop. We've already incremented y. And here, because we did this push A, if A is 0, then we know we've gotten to the end of the original string, because this is a null terminated string. So we can do a conditional branch here to jump back up to the beginning of our loop. All right, so we're initializing our y counter to 0, and we've got this loop. We're going to go through this loop until the value that we pull off the beginning of the string is a 0, and then we're going to drop out of the loop. But otherwise, what we're doing is we're going through this loop, and then each character in the string is getting pulled off, eventually pushed onto the stack, and we're taking whatever was on the stack and putting it as the new character in the string. And so and this is going to have the effect of sort of shifting everything to the right in the string, and then adding the whatever we entered the push character subroutine. We're going to add that as the new first character at the very beginning of the string. So at this point, at the end of the loop, we've shifted everything along. We've gotten to the end. We still have the null terminator for the string. That's still on the stack, so we can pull that off into the A register. And then add that to the very end of the string. So that way we have the null back at the end of the string, so we're coming out of this subroutine with a null terminated string. The only thing we've done is we've just added the new character to the beginning of it. So we can return from subroutine, and that'll bring us back up to here where we called this push character. And so now when we get to the end, right before we would go into this infinite loop, we now have this message that we've created, which is a null terminated string that has the ASCII representation of our decimal number. And so now we just need to print that. So I'm actually going to go ahead and open up the old Hello World program, because that's already got the code in it to print the message, right? Because we had this ASCII null terminated string that we printed out, Hello World, or whatever message we wanted to print. And we've got the code right here that actually prints that. So I'm going to copy that and hop back over here, and I can paste that in. And all this is doing is it's saying, load a 0 into the X register. And then we're going to go through a loop here where we load each character of message into the A register. If we get a 0, then we jump down to our infinite loop here and halt the program. Otherwise, we print the character that we loaded. Then we increment X and then just jump back up to print here. So, we're just incrementing X so we can get to the next character in message. And so it's just going to print everything starting at message until we get to a null. So because this push character is constructing a null terminated string, this ought to print that string out. So let's save that. Run the assembler, get our EEPROM back in the programmer here, and program it. But anyway, there we go. We're all programmed. So let's put this back in. I guess I maybe should have powered this off, but whatever. Reset, and there it is, 1729. It worked. And so there you have it, converting binary to decimal. How hard could it possibly be? Apparently it takes 164 lines of assembly code. Who knew? And if you'd like to play around with building and programming a computer like this yourself, you can get kits for this and other projects over at my website, eater.net. And it's been challenging with the pandemic, but I'm happy to report now that everything is currently in stock and ready to ship. But of course, check out eater.net/shop for the latest. And of course, thanks to all my patrons. Your support is a big part of what enables me to make these videos. So thank you.